So when we talk about industrial control systems, they always consist of two parts. You have a communication infrastructure, which is governed by the science of, by the computer science. This is where people who study informatics are basically managing those systems. And we have physical process where the science of engineering, and sometimes we call this OT or operational technology. And the process of the attacker is in the physical world. To do some effect in the physical world. Simply, if the attacker simply hack into the plant and just is there and does nothing, there is no damage, there is no harm. So the attacker is going into the plant to cause some physical damage. And this is why when we talk about industrial control system security, it consists of two parts. One is IT security, basically taking over the cyber infrastructure, and then the OT security is causing impact on the operations, basically process or physical equipment. And this is what constitutes the attack payload. So in order to understand how to design this cyber-physical damage payload, the most important thing to understand is the concept of control loop. So all plants work on the concept of control loop. So you have your desired set point. For example, you want to maintain a temperature at, 21 degrees, it's comfortable. So then you have a sensors which measure the state of the process, control system which calculates the difference between desired and current state, and then it's calculate the control command to the actuators, which could be valves, pumps, or whatnot. But a single control system can never control the entire plant because they only have a local view. Therefore, we need human operators which have a global view of the physical process. And if the control system is incapable of maintaining the process in a proper state, the human operators will take over. And on top of that, we still have, so there's basically this next level of hierarchy, we have process optimization, which is a complex applications which make a lot of advanced calculations in order to predict where the process is moving and to make basically some predictions and to take corrective actions. So those systems are even smarter than the HMIs. And when we talk about architecture of industrial control system, of real, like this is, for example, I think it's Honeywell system. So they actually built to represent that hierarchical control system. So we have at the bottom physical process, then we have controllers which are regulatory control, then we have HMI, the human operators optimization application, and on top, of course, you have planning and management, like where do we want to be in 5 years? And the definition of real time, basically the real time is becoming larger from the bottom to the top. It means the control loops at the regulatory level work on the real time of nano and milliseconds. The HMIs work already on the terms of minutes or like 30 seconds. And when we talk about optimization applications, those could be days, weeks. So, for example, therefore, for the attacker, in order to, for example, modify some parameters in optimization application, does make sense, because the effect will show up only maybe in a week time, and it might be not even the same effect. You cannot quickly make corrective actions. It's also might not be so, for example, if the attacker tried to manipulate the system at the HMI level, the controllers may override those commands because they are moving faster. They are issuing commands much faster. Therefore, for a very granular, a very precise, very reliable attack, that, the attacker wants to be in the controllers. So, and controllers is already not a normal PCs. They are embedded systems. So depending on the physical process, whether it's chemical plant, power, or robotics, they will look differently. But at the end, it's just an embedded system with real-time operating system. So the attacker would need already to write exploits for embedded systems. And this is why the attacks on the industrial control systems are called cyber-physical attack, because you need to do something in the cyber world to cause an impact in a physical domain. Absolutely very brief history of cyber-physical attacks. We can trace it back almost to 1999, where certain nation state already, so first of all, we already have seen intrusion into the industrial facilities, but also certain nation state already successfully executed cyber-physical experimentation, like offensive security. Then in 2010, probably everybody heard about the Stuxnet. Interestingly enough, Stuxnet, with the new findings, the Stuxnet preparation started in 2003. So all of those work which was done before, like in the past century, was leading towards that certain nation states were already able to execute such an attacks like Stuxnet. Then we have a HAVEX, which was basically automatization of the reconnaissance capabilities for industrial control systems. I really love that exploit. And then 3 years in a row, we had 3 cyber-physical attacks happening in the real facilities in the world. We have 2 Ukrainian power grid attacks, and then we have Triton, which was targeted safety instrumented system. A short what has happened, so the attacker obtained remote access to safety instrumented system, and there was dual home safety engineering workstation, and through that the attacker gained capability to interact digitally with safety controllers. So what Triton does, basically the attacker attempted to inject a passive implant into the Triconic safety controller. Attempted means they were actually unsuccessful. They were not, at the end, they were not able to inject it. What means passive implant? It means that this code, if injected, it actually does nothing. It's a remote access Trojan. It just sits there in the memory and waits for the further commands. So that Triton implant can read, write, or execute memory. So for example, if the attacker later wants to bring the damage payload, they will bring a code, the Triton implant will write it into the memory and then later execute it. Basically, Triton, the safety controller becomes a slave. How critical it is, just to re-emphasize. So Triconic supports so-called safety integrity level 3. What does it mean? So if you see this graph at the top, this is a classification of all control loop in a refinery, no-name refinery in Middle East. And as you can see, only 2% of the control loops require this protection of SEAL 3, which is Triconics. It means this is the most, SEAL 3 means that these systems are so reliable that they almost never fail. Deploying such system, installing them is extremely expensive because they're super complex, super reliable. So therefore, they will be only used on the most critical control loops, like those which are where there is a danger of toxic releases, explosions, and so on. So they really protect civilians from basically death. So what is a Triton worst case? So what would be like if the attacker would successfully inject the implant? So this is the electronic board of the safety controller. And the way how the safety controller is designed is that the main processor of the controller and the communication processor, they are actually located on the same electronic board, and they communicate with each other via the shared memory. So with just really literally a couple lines of code, the attacker can already write any command to the input-output card. So he basically can manipulate final elements like valves at will. And with the highest privileges, like basically with privileges higher than the firmware, with the operator, control logic, and so on. So he owns it. So basically, when you will have unsafe situation and the valves should close and contain the process, the attacker can keep them open, and you will have a safety incident. So now, if we will map all of this, three attacks against that traditional industrial control systems with which I showed you before with the definition of real time, we will see that with each attack, the attacker was moving their exploits one layer down. This concept is called race to the bottom, and it comes from the traditional IT security domain, which means that as soon as security protections are introduced at certain layer of network or computer architecture abstraction, the attacker is moving their exploits one layer down, where there is no protection. This is also let's say this concept and thread is also supported by the fact how the attackers are now trying to get access into the industrial facility. So traditionally, and even in the case of Triton, the attacker was trying to get into the facilities through the front door firewall, basically from the internet through the firewall, and then moving through all the layers of networks until they reach industrial control networks and systems. But this is where, if the attacker will go this way, there are a lot of security mechanisms installed typically at level, like in those layers. of networks, and therefore there is a very high chance for the attacker being detected. So therefore, the attackers increasingly are going through the trusted third parties, like vendors, supply chain, subcontractors, remote support, and so on. And with that, the attackers are immediately landing already in the plant, in the industrial environment, on the safety engineering, like on the engineering workstations, and they already can directly inject implants or payloads into, for example, embedded systems. So the attackers are really going this path. So what shall asset owners do? Because there is a problem, yeah? The attackers are increasingly already going through the staging targets directly into the industrial environments. The assets are unprotected, so then what shall asset owners do, like owners and operators of industrial facilities? So first of all, it's really time to get angry. So Andy Bochman just left, but like we've talked today about that, it's been already more than 10 years, if not 15, since the community was screaming for improving the security in the devices, and nothing is changing. And somehow the community asset owners, they're still kind of nice and kind and understanding and forgiving, and this is why I'm saying it's time to get angry. We need to start demanding from the vendor that they do something, because there is enough knowledge base available to improve security, or at least implement exploit prevention mechanisms in the embedded systems, in the firmware. So, and we really need to be worried because the barriers for cyber-physical exploitation has lowered substantially. Previously, you would not be even able to buy any of those safety systems, because in order to develop exploit, you need to have equipment in the lab. Previously, you would not be even able to purchase this equipment if you are not a lawful owner of the, not coming from the industrial domain. Right now, you can buy anything, absolutely anything on the free market on the internet. You can buy safety controllers, you can buy software. For example, for that Triconics, we bought software. This is our own picture for $3 in the Alibaba, the entire industrial software. And I was able to find even a source code of that controller, which was not easy, but it's possible. So the attackers already have all necessary resources in order to design exploits for industrial control systems. This is the, for example, while working, doing this forensic work on the Triton exploit, together with the researchers from Nozomi, we found in the software that there was undocumented user with very, very high privileged rights. And again, the asset owners, they don't know that the user even exists because it's not documented. But with those privileges, there are actually a lot of bad things can happen. And so it gives attackers super powerful access, and that those super privileged rights even have a name, backdoor. So it is critical, as I already stated, to develop embedded systems, auditing, and forensic tools before exploits like Triton become common. So we need, for example, this monitoring and auditing solutions, did somebody tamper with my device? Is my firmware changed? And then we need also forensic tools after we already know that somebody tampered with my device. What exactly has happened with my device? Basically, to support the forensic activities. This also indicates for us already that establishment of multidisciplinary attack teams. So defending against such an attacks takes also multidisciplinary teams. But to date, the defenders mostly if we talk about industrial facilities, defenders mostly IT guys who doesn't appreciate really the control system part. Few takeaways on Triton. So very highly likely, with a very high probability, Triton-like capabilities were developed not only for Schneider systems, but for systems of many different vendors. And as I already mentioned, the formation of what we've noticed, a formation of multidisciplinary teams, and this is what we also need to do for defenses. What was extremely bothering me, Triton was detected during the attacker effort to inject the implant. And the attacker was debugging exploit on a live system. So on one hand, it's really, I would say you need to be very brave to debug your code on a live system. I mean, and we probably will see more of that because not only that, sometimes not all the attack teams may have all necessarily equipment in their lab, so they need to practice and exercise on debug code on the live system because they just don't have it in the lab. But but on the other hand, for us, for the defenders, it means that while they are debugging, we have a little bit of time. If we are watching and know what to look for, we have a little bit of time to detect, and then Triton could have been detected. And security is a fashion industry. As soon as some type of kind of exploit is being thrown in the wild, everybody's starting copying. It's just like, so these copycats, so multiple, like many other different threat actors will now start developing similar type of exploits.